So hi there, this is Amir and I want to walk through the TiLens approach, which is a model agnostic approach to define the important tiles for prediction tasks in machine vision. So it is also like created for vision language models. And the problem with many of these vision language models is that you can't really go deeper with model weights and see what's going on inside the machine logic. Although machines are not working in like similar to human logic, but it would be nice to have an idea of what's going on. So this is TiLens. We have two approaches. I will first walk through the approach and then run the code for one example image. So the whole idea of creating these heat maps, let me show you the output first. So this is the example of the output so far. This is the original image showing a UC patient with a Mayo endoscopic score severity of 2. We can have classes of 0, 1, 2, or 3. And by 1, 2, and 3, I mean if the severity of this disease is like mild, moderate, or severe. So this is the original image, and first we will create some masked instances like this. So this is our 2x2 sliding mask, and we will assume that if we mask an error and if the output changes, that mask error has a more like importance. So it is not about the ground truth, but about changing the image answer when we mask one region. And we will also try like generating output for each masked image multiple times so we can create a probability of each region. Selecting one image for testing the TiLens is important. So the image should have the ability to be masked. And I mean, if we mask one area of the image, one tile, this tile should cover the ground truth. For example, in this, this tile is like working good with hiding the ground truth of this image. So this is the whole idea. So we will first create masked regions of each image, then we will run the model on each image, and now we will know and when we know the input and outputs, we can create the heat maps, which is like this. Like this one. Yeah. So the red arrows shows the most important regions, and this is the XAR lens with consistency normalization. So with vision language models, we can get like different variations in the original image. So the base approach, which is like XAR lens, will assume the base response as the most prevalent answer. And for sure, if we have multiple answers with equal number of repeats in the output, there's this is a problem we should solve, and we should run the model more to see the outputs, to get one base answer and calculate these regions. But with the XAR lens with consistency normalization, we will also include the inconsistency with the model output given the original image. And this is important. So yeah, for example, this one, as you can see, for this one, the XAR lens output is not that much different with the consistency normalization, since the model output was consistent on original image on multiple runs. But for this one, as you can see, there is a big difference between XAR lens and XAR lens with consistency normalization, since there was an inconsistency in the original image. In the future, we will also add XI lens with consistency normalization and log probabilities, which I will introduce in the future. So this is the mathematical background on each approach, how we create these masks and how we create the heat map overlays, and the summary. Same goes for the second approach. The biggest difference is about the consistency of the answers. So the biggest difference is that in the base approach, we will find the base answer, which is the most prevalent or most consistent answer. But for the second approach, we will try this method. So we will compare the dictionary of outputs and their repeats in the original image, and we will compare the answers to that output dictionary. So this is the biggest difference. Let's move on with the code. So first of all, you should place your image inside one folder and define this folder inside here, and the rest is semi-automated. So when you define the location of the image, the rest is you should just run the code and see what happens. The other thing that you should define is this. So yeah, let me make it more comprehensible. So the next thing you should define is the number of runs you want to have. In my experience, 7 is the best number, but if you set this to higher amounts, the cost of calculating these tiles would be higher. But I will go with 5 to have lower cost, but 5 is the minimum, 9 is the best, 7 is the optimum point. In my experience, we will have a paper, and I will put that in the GitHub repo, and it would be awesome if you can start a repo and cite that paper. That's the ultimate goal of a researcher, I guess. So yeah, so for this example, I want to get output for each image, for each masked image 5 times. And this is the tool to force the LLM to give us only 2 options. I don't want to chat with the LLM, so this is not the prompt. You should not embed long instructions here. This is just the tool name is polyp detection. You should not have spaces or any other string other than words, numbers, and underline here. Let me add it here. Only words, numbers, and underline, which is this. Then you can define the description. So this tool will choose one of the mentioned options to tell if any polyp exists in this image. And the options are polyp visible and polyp not visible, for example, in this case. Also, selecting a good image for doing XAI is important. You don't want to apply this to the whole data set. You just want to find some relevant, good examples to see if, for example, in this image, if the model can see these polyps or not. And this is a really good example, since this is not a good one. So here, if I mask this tile, I should still get the output for these regions. So you should choose something that you can mask. Still, those maskings should make a change for the output and see what happens. So this one is not a good one. Let me replace it with another image. So this is the next image I chose. I want to see if the model will, this device will make the model to think there is a polyp in this image or not. I have no idea about the output. So yeah, this is it. These are you should also install many libraries like Peel, OpenAI, and Pandas. These are like embedded within each like Python, but you should like, this is OpenAI, you should install these things before running the code. So I hope I should have a requirement.txt file for you guys. So when you're done with this, you can proceed. So let me just run this. I already made some difference, some like hashtagging. So the first section will create masked image. These are the functions for masking. This will mask the tile. This function will blur the tile. This is the function to process and create the image. So in my experience, 2x2 sliding mask with the mask output is the best one, but let's see what happens. So if I do like 2x2 masking and use mask option, the outputs are like this. So I can also go with like by 2x2, I mean the width and height of the mask tile would be half of the image original size. So if we try blur, the output would be like this. So you can see the outputs. Sorry. So let me correct these file names. One, I will store the image dict, and this is for my own use cases in the future if I want to. So one is this, two is this one. So I can also make another, yeah, let's make these things easier. Yeah. So blur, mask, so it will generate these masked images here. Blur, mask. Oh, you can also go with a sliding false. Let's see that. So this is a static, which means that there is no overlap between the tiles. Let me remove them. I don't want them. This is the blurred version. So we will blur the image in case that it works for your own context. In my case, mask is the suited option, and to be honest, you should set this sliding as true always. And you can also play with these things also. Yeah, as you can see, it's like the masks are different. You are the person who should design and find the best scenario for your own case. In my case, this scenario will create like good masks. It will hide the ground truth in this example. This example is also good, I guess. And then we should see what happens. There is another approach which I should like add to the pipeline to have mix of these mask tiles to, for example, if I want to mask these two regions, this region and this region, I can also create like add image manually here. But you should define the image coordinates, which needs like a little bit of time for you guys to change the code. Hopefully I will add them to the next pipeline. So when you are done with this, let me get back to, so I created a sliding mask by 2x2 tiles. Then I should create an empty Excel file. And when you run this code, sorry, yeah, when you run this part, the Excel file will be opened and it will guide you to define the prompts. These are the scenarios you want to play with. You can also do adversarial attacks here by defining like some tricky prompts. I mean, if what happens if I ask the model to explain why there is no polyp in this image, for example? What happens when I ask the model to tell me why there is no polyp in this image while there is a polyp in this one. These are some adversarial attacks. You can add them here. We will use this to generate the outputs and store them in these columns. You should avoid setting the seed, because when you set the seed to some number, it will cause some consistency with the outputs, and we can't really see the variation within the model output and create the output probability by having multiple runs. So don't set the seed value to any thing. So yeah, let me find my prompt. I should have a prompt here. Let's write it down. You are tasked. Oh, this is a colonoscopy image. You are tasked with classifying this image as polyp visible or polyp not visible. So there is no like prompt engineering technique. You can go with anything that you want. But the cool thing about my code is that it will trick this tool call will force the model to give the output as polyp visible or polyp not visible. So if you just go with the base pipeline, you will get answers like there is no, like, I can't answer this question because I'm not like a medical professional or something like this. But now we will force it to do this classification task. So when I define the prompts, I can also define different temperatures, but you can play with these things to do attacks, to find like the impact of max completion token and temperature on the outputs. But for our XAR lens, you should not change these variables. Or if you want to change anything, make sure that it is like similar between all of these rows. Because what we are doing is to create 5 answers for each image and then store them here. And these are the x and y coordinates of each mask tile. So we will use these x and y coordinates to create the heat maps at the end to find the like important tiles. I guess that's it. Let's move on. So I defined the, let me just check. Yeah. Oh, I forgot to press the save button. This is a colonoscopy image. You are tasked with define whether a polyp is visible in this image or not. You should base your classification on mask, like on available regions or available information, for example. I will do this for all of these things. So it's done. Now we should generate, this function will generate the output. This function will encode the local image. This will set system message. This will set the text, like the prompt you just mentioned, you just like defined in your Excel file. This is the image URL. This is the tool call. This function will extract values from the VLM response. This is an asynchronous call to run the OpenAI chat completion crate and use the tools and messages that we defined, and then clean the output and return the index status VLM response. This is the raw response. The clean class, which is the chose class from those two options, This is the number of completion tokens and prompt tokens. And this index refers to the row index. Since I'm using async def, I want to use this to store the outputs. Yeah, this is the unit test. You can test this function here. Let me just show it to you. You can define the this is R2, and these are the parameters for this unit test. This is just a unit test. You can skip it. It will tell you that this function is working or not. I'm using GPT-4o for visibility of polyp. This is the prompt. This is the temperature and seed, so I don't want to set the seed value. Or set the seed value to none. This is an example index. This is the location of the image. Let me show you. Yeah, this is the path to the one example image. This is the client, and all other things are fine. So yeah, sorry, I forgot to run this. I forgot to run something here. Yeah, it's working. So for this image, the output is polyp visible. It can see the polyp. So this is the Excel handler. Let me hashtag this file. So I deleted these files to show you that the only thing that you need to run and define are these things inside the main XAI lens here. And if you can see, when you run this, it will do all of the aforementioned steps. This is a colonoscopy image. You are tasked with classifying this image if a polyp or not. Base your classification on the given regions, on the visible regions. This is just to make sure that the model will give me the output, and don't say that, like, don't avoid to providing the output if it can't see any region. And I should define this for all of these rows, save the file, close the file. So when I get back to the file, it will ask me to define the prompts. I already defined them, so you can press anything and it will start generating the output. So there is total of 20 images, and each one will have 50 like five similar runs, which would be like 10 runs. And when the generation is done for each image, you can see the outputs here. And you can also change the OpenAI function to include any vision language model that you want to use. Yeah, so it's quite fast. I tried to do asynchronous calls, but it is not working yet to send a parallel request to OpenAI. So this is the answer dictionary. This is the answered file. This is the empty design. This is your design to run your pipeline on. And let me just copy and paste this answered column, this answered Excel file. So this is the answer status. If any error happens in the code, you can see it here. And the code will avoid doing like redoing things. And this is the raw response. This is what you get from the chat back from the ChatGPT's server. This is the number of tokens and number of prompt tokens. This is the the class that it defined. So for example, if anything happens, let me stop this and let me get a backup of this answered file. But if anything interrupts your code, if you want to like pause the code, you can see that it would be a stop. So if you open the file, these are the given answers. So if I run the code again, but not the whole code, the last part, this part that will generate the outputs, this part, it will ask me if I want to continue with the previous answer file or overwrite and use the new design. Since I want to continue, I will press the continue and it will continue to do the like at index 35. It will continue the generation. So let me just introduce the next codes. So here we will generate the outputs. This is for the attack. I haven't completed these attacks yet. These are the output and visualizations. To create the XAI lens heat map, we will first find the base answer for the original image, which is the most prevalent answer. Then we will calculate mask importance, and by mask importance, we will give 1 point for each different answer in the masked image compared to the original base answer, to the like most consistent, most prevalent answer on the original image. For example, if all of the 5 images, like 5 similar ones on one masked image are different than the base answer, the tile will get the score of 5. Then we will normalize it to get the like mask importance of 1. We will do this here. So mask importance is from 0 to 1 in both XAI lens heat, like XAI lens base and XAI lens with consistency normalization. So this will create the heat map. Here you can see the normalization here. The normalized importance is importance divided by desired enough runs. So if like 5 runs are different from 5 runs, the normalized importance is 1. But for example, if 2 of those 5 runs are different than the base answer, it will get the a score of 0.4. And we will use that to create these heat maps. Let me see if it's done or not. No. The difference between like the XAI lens base, this one, and this one is, the name is con-norm. In the second approach, in this approach, XAI lens with con-norm, consistency normalization, we will get the output of all answers and their cons. Instead of assuming one base answer, we will get the cons of all answers, and we will use that to define the mask importance. So if the answer is not among the given answers, if we have, for example, 5 classes, if the given answer on each mask row, each mask image is different than any of those answers, the output will get a score of 1. But let me tell you. So if I run the VLM, Vision Language Model, on original file, and if I have, for example, 3 classes, and in 5 runs I get 2 answers on class 1, and I get 3 outputs on answer 2. On each mask tile, if the output is 3, it will get 1, 2, 3, For 3, it will get the score 1. But for 2, since 3 out of 5 answers in the original base image are 2, it will get 2, like, let me write it like this, 5 minus the number of repeats in the original image divided by the total runs. And if the output is 1, it will be 5 minus the number of answers in the base image divided by 5. So it's like a consistency normalized output. If the output is like consistent on the original image, it wouldn't be that much different. So it's done. So now that it's done, we should see, yeah, all of the outputs are okay. In some cases, you may get errors in this column. On those cases, you should go through this and find the defined class here. Yeah, no errors so far. Let's move on. Yeah, so this code is done. I should go with this code. It will create the probability, like for the first answer, the most prevalent answer was polyvisible. Same goes for the second answer. Then we will create the mask importance, and you can see the mask importance is also here. So for each masked image, we will calculate the importance, and then we will use it to show the outputs. I love to see the heat map of this. So yeah, when you sorry. Yeah. So when you run this, create the heat map, where is that? I am lost. Yeah, it's fine. So when you run this, you should see 2 images. Yeah, in my opinion, the output is good. Let me decrease this to see. Yeah. So the most important tiles are here, and for this one, the most important tiles are here, and it's really good. And it will also store these images as like XR lens heat map. And let me run the next code. This code will give you the counts of each output, and since all of the answers was polyvisible, you will not see any difference on the heat map. Yeah. So it will also store something like this, mask importance with consistency normalization. Yeah, but it's the same since all of the answers on the original image was consistent, so there is no big difference. And yeah, and this so here for creating the final figures for your paper, you can define the original image, XR lens, and XR lens consistency normalized here. So let me quickly, in Windows, if you press Control Shift and C, you will get the path to the image. And make sure that you put R before this. So you can modify the code to have a smarter ways to create this one. It is not like smart at all, but it's useful. Yeah. Here. So if you define these tiles, and yeah, this code will create the final figures for you. This is the figure like on the image, on the first image. So actually like these tiles are also helping the image to provide the output. This is also cool. Yeah. Oh, I defined the incorrect file for the last one. Sorry. Yeah, this is incorrect. The last numbers should be 71. Okay, now it's so as you can see, there is no difference between consistency normalization, as all of the answers on original image was consistent. But you will get some different results if you go with more like complex scenarios. For example, this one. And that's it. I hope that I can build on top of this to add log probability and future adversarial attacks to make it easier for people to get the like sense of what model really sees on these prediction tasks. Yeah. Oh, also the code is available at TiLense-4blacBox-VLMs here, and that's it. Keep safe, and I wish you all success with publishing something somewhere. Bye bye.